have our final exam schedule from the registrar. It comes Tuesday morning of exam week. It's on the web page. You won't miss it. I want to remind you that the midterm exam is on Wednesday, March 16th, that it starts at 9, not at 9:30, so that you're less time limited than you would be otherwise. It's a 2-hour exam, and it will cover basically up through Chapter 8, which is Reed-Muller Codes, and you're responsible for anything that's been discussed in class. If we haven't discussed it in class, then don't worry about it. All right, any questions about any of those things? Let's see. It's 9 o'clock to 11 o'clock. What's the underline? This line up here. This says this class goes from 9:30 to 11. Not 11:15. That's for me, not for you. Although I've tried to lay off some of the responsibility on you. Okay, let's continue. I hope to finish up Chapter 6 today. Might not completely finish it. There are really 3 topics left to go. One is the orthogonality and inner product topic, which I skipped. The second is the Reed-Muller Codes, which is our main objective in this chapter, a family of useful codes. And the last topic is why making hard decisions is not a good idea. And so I'll try to say as much as I can about those 3 things. Just to remind you of where we are, we're in the power-limited regime. We're trying to design good small signal constellations or moderate-sized signal constellations now with nominal spectral efficiency, less than 2 bits per 2 dimensions. The technique we're using is we're going to start from a binary linear block code in Hamming space, and we're going to take the Euclidean image of that and hope it's a good constellation in Euclidean space. And as we were just talking about before class, the fact that a linear code is a subspace of f2 to the n means, it's true if and only if, really, it has the group property, which in Euclidean space leads to a geometrical uniformity property. We haven't proved that in its full scope, but we have noticed that from every code word has the same distance profile to all other code words. And in particular, the minimum distance is the minimum weight of any non-zero code word. That's the main juice we've squeezed out of that at this point. We've now been talking a little bit about the algebra of binary linear block codes. We've characterized them basically by 3 parameters, n, k, d, where n is the length of the code, k is the dimension of the code, d is the minimum Hamming distance of the code. In the literature, this is what you'll mainly find, an NKD code. We have a subsidiary parameter, the number of words of minimum distance d, which we're going to need to get the error coefficient, our union-bound expression. This has less prominence in the literature. Given just these numbers, we get a couple of key parameters of our constellation. One is its nominal spectral efficiency, which is 2k over n bits per 2 dimension, upper bounded by 2. Of course, often in the coding literature, you talk about a more natural quantity, which is k over n, called the code rate. Maybe I shouldn't call it cap r, because r is used for the code rate in bits per second. This means bit per symbol. So just let me call this rate. But when you're reading the coding literature, the rate of the code means how many information bits per how many transmitted bits. And for NKD binary linear block code, it's k over n. And the nominal spectral efficiency is just twice that, because we measure it per 2 dimensions. Okay, and even more importantly, we get the union-bound estimate in terms of a couple of simple parameters. It's just an error coefficient, KB, the number of nearest neighbors per bit, times this Q function expression, which always has 2EB over N0 in it, multiplied by this multiplicative factor, which we call the coding gain, which is just KD over N. And this is equal to 1 for a 111 code, i.e. no coding. Anything else? Our basic effort is to get a larger coding gain by constructing more complicated codes. This parameter here, which we need in order to actually plot the curve and estimate the effective coding gain. The effective coding gain is derated from the nominal coding gain by a rule of thumb, which depends on KB. Basically, every factor of 2 in KB costs you 0.2 dB, roughly in the right range. If it's not too big, all those qualifiers, but it's a good engineering rule of thumb. And that's just the number of nearest neighbors per code word divided by K. And so our object here is to see how well we can do. And the Reed-Muller codes will be an infinite family of codes that give us a pretty good idea of what can be achieved as, for a variety of N, K, D that kind of cover the waterfront. That's why I talk about them first. They're also very simple. Okay, but first we forgot to talk about orthogonality and inner products, and duality, both from a geometric point of view and from an algebraic point of view. And so I want to go back and recover that. The definition of an inner product between x and y, where x and y are both binary n tuples, is, as you'd expect, a sort of dot product expression, a component-wise product, the sum over k of xk, yk, where all the arithmetic here is in the binary field, F2. Okay? And you can, this clearly has the bilinearity properties that you expect of an inner product. It's linear in x for a fixed y or vice versa. But it doesn't turn out to have the geometric properties that you expect. We can define orthogonality. This is another definition. In the usual way, x and y are said to be orthogonal. Do that better. X is said to be orthogonal to y if and only if their inner product is 0, which is the same definition you know from real and complex vector spaces. Okay, but this the overall moral I want you to get from this is, while this inner product behaves absolutely as you expect in an algebraic sense, it behaves very different from what you'd expect in a geometric sense. So the algebra is fine, the geometry is screwy. All right, that's the catchword to keep in mind. Why is that? Where does this inner product live? It's F2 valued, right? I'm just doing this sum in binary space, and the result is either 0 or 1. So when our two code words orthogonal, it's simply if they, two n tuples orthogonal, it's simply if they have an even number of places in which they're both equal to 1. Is there a question? No. All right. In particular, suppose I try to define a norm in the usual way, like that. Is that going to have the properties that I want of a norm? No. Why? Because one of the basic properties we want of a norm is strict positivity, that the norm is equal to 0 if and only if the norm of x is equal to 0 if and only if x is equal to 0. That's clearly not true here. What's the requirement for the inner product of x with itself to be equal to 0? In other words, x to be orthogonal with itself? Just simply has to have an even number of 1s. If it has an even number of 1s, then the norm, this so-called norm, is 0. If there's an odd number, it's 1. So it's perfectly possible for a vector to be orthogonal to itself, a non-zero vector to be orthogonal itself. And that's basically where all the trouble comes from, all right, in a geometric sense. It's mod 2. It's in F2. All the arithmetic rules are from F2, which is mod 2 rules, correct. So good. This means at the most fundamental level, we don't have a Hilbert space here. We don't have a projection theorem. Projection theorem is the basic tool we use in Euclidean spaces, more generally Hilbert spaces. Just say that every vector can be partitioned. You know, given a space and its orthogonal space, we can express a vector as the sum of its projection onto the space and the projection onto the orthogonal space, which are two orthogonal vectors. So it's an orthogonal decomposition. So we have nothing like the projection theorem here. Therefore, we have nothing like, we don't necessarily have orthonormal or even orthogonal bases for subspaces, yeah?
So you don't have projection theorem because you don't have a unique orthogonal complement.
You do have a unique orthogonal complement. I'll get to that in a second. For instance, we might have that a subspace can be orthogonal to itself. That's what the problem is. For instance, 0, 0, and 1, 1 is a nice little one-dimensional subspace. And what's its orthogonal subspace? It's itself. Okay, so we may not have an orthogonal basis for a subspace. And for an example of that, I'll give you our favorite 322 code, as I'll now call it. It consists of these 4 code words. A set of generators for this code consists of any 2 of the non-zero code words. We can generate all of the code words as binary linear combinations of any 2 of these. But no 2 of these are orthogonal. All right, so there's clearly no orthogonal basis for that code. So we shouldn't expect to find orthogonal bases, orthogonal decompositions, all of these sorts of tools that we relied on heavily in 6450 in Euclidean spaces. Okay, so this is just a great caution to the student. Don't expect Hamming space to have the same geometric properties as Euclidean space. Yes?
Is the problem going to be there in any finite field?
Yes. Nothing special. It's just finite fields have a different geometry. In F2, there's really only one geometry you would impose, which is the Hamming geometry. In other finite fields, there actually could be more than one geometry. But let's say the algebraic properties, however, you can still count on. For instance, NKD code C has, as we've already shown, a basis, has k dimension, has a basis G1 up to GK of k linearly independent, though not necessarily orthogonal, basis vectors. So we can always write the code as the set of all UG such that U is a k-tuple of information bits. Let's say, in other words, this is a compressed form for the set of all binary linear combinations of these generators, where I've written what's called a generator matrix, G as a k by n matrix, whose rows are these generators. And I've multiplied on the left with a row vector u, if I'm doing it in matrix terms. You know, I view this more abstractly, just as a linear transformation. And side comment, notice that in coding theory it's conventional to write vectors as row vectors, whereas in every other subject you take, it's conventional to write vectors as column vectors. Why is this? Is there some deep philosophical reason? No, it's just the way people started to do it in coding theory back at the beginning, and everybody has followed them. I may have even had something to do with this myself, and I'll tell you the reason I like to write vectors as row vectors is I don't have to write a little t up next to them. That's the deep philosophical reason. You know, it's like driving on the right side or the left side. Obviously, you could have chosen how to do it one way or another back in the beginning, but once you've chosen it, you better stick with it. There's actually, you know, some insight involved here. This is sort of associated with a block diagram where we take k bits and we run it through this linear transformation, and as a result we get out what shall I write? X n bits. And in block diagrams, we tend to take the input bits from the left and proceed to the right, left to right kind of thing. So this formula kind of reflects this left to right picture, whereas I'd say the deeper reason why you usually see GU in system theory is that G is regarded as an operator that operates on U. It's kind of G of U. And so that's why it's more natural to think of this as being a column vector, because then we have a different picture. G is the operator that somehow transforms U. But these are all side comments, obviously don't really matter for anything. All right, just remember that vectors are row vectors. Okay, let's define the dual code in the natural way as the orthogonal code. Say C dual. The definition is that C dual is the set of all y, set of all n tuples y, such that x, the inner product between x and y is 0. In other words, y is orthogonal to x for all the x in C. It's a set of all n tuples that are orthogonal to all the words in C under our F2 definition of inner product and orthogonality. Okay, so that's a natural definition. For example, as I've already shown you, if C is 0, 0, 1, 1, then C dual is 0, 0, 1, 1. If C were 0, 0, 0, 1, then C dual would be 0, 0, what? 1, 0, thank you. Because 1, 1 is not orthogonal to this, and 0, 1 is not orthogonal to this. So we just simply go through and pick it out. Now, as I said, the algebraic properties of the dual code are okay. I emphasize they're algebraic. If C is an nk code, in other words, has dimension k, what are the parameters, what do you expect the parameters of C dual to be? Its length is what? It's n, of course. And what's its dimension going to be? If C has dimension k, what do you guess the dimension of C dual is going to be? Just guess from Euclidean spaces or any. It's n minus k, right? The dual space has dimension n minus k. And that holds. In the notes, I give two proofs for this. There's a conventional coding theory textbook proof, which involves writing down a generator matrix for C, k generators, reducing it to a canonical form called the systematic form, where there's an k by k identity matrix in it and a n by k, n minus k by k parity check part. Then by inspection, you can write down a generator matrix for C dual, and you find it has dimension n minus k. It's kind of a klutzy proof, in my opinion. A second, more elegant proof, but one that you don't have the background for yet, is to use simply the fundamental theorem of homomorphisms. This is, in some sense, an image. This is the dual of an image, which is a kernel, and you work out the dimensions from that. I am still in search of an elegant elementary proof, and anyone who can come up with a proof suitable for Chapter 6 gets a gold star. Believe me, the gold star will be very valuable to you. Okay, so exercise for any student so inclined. Give me a nice proof of this. It's surprisingly hard, and I can't say I've spent great quantities of my life on it, but I've spent some time on it. So, anyway, the dimensions come out as I hope you would expect based on your past experience, and I won't give you a proof in class. You get the fundamental duality relationship, the dual of C dual. What do you expect that to be? C. Okay. In words, C is the set of all n-tuples that are orthogonal to all the n-tuples in C dual. Okay? So this actually means that I can specify C. If I know C dual, I know C. All right? Give me C dual. The set of all code words orthogonal to it tells me what C is. So this implies that I can write C in the following form. C is the set of all, just emulating this, y in f2 to the n, such that x, y equals 0 for all x in C dual. I probably should have interchanged x and y for this. X such that x, y equals 0 for all x. This is symmetrical. Inner product of x and y is equal to the inner product of y and x. So I don't care how I write it. Okay, so I can actually specify a code by a set of parity checks. Now, suppose I have a generator matrix. Let me call it H, namely a set of generators H1 through Hn minus k for C dual. I'm going to have a set of n minus k generators. Then I hope it's obvious that I can test whether x is orthogonal to all the generators, to all of C dual by just checking whether it's orthogonal to all of these generators. So I would now have C is the set of all x n tuples x such that x h j equals 0 all j. Okay, I've just got to test orthogonality to each of these generators. In other words, and each of these is what we call a parity check. We take the inner product of x with a certain n tuple and we ask whether parity checks. In other words, we ask whether the subset of positions in which hj is equal to 1, in those positions, whether x has an even number of ones. Get very concrete about it. So, writing this out in matrix form, the test is C is the set of x in F2 to the n such that x h transpose equals 0. That's just a matrix form of what I've written up there. So let me picture it like this. Here the test is I take x, which is n bits, I put it into what's called a parity checker or syndrome former, and I ask whether this is 0. We call this in general the syndrome, and we ask whether it's 0. If we get a 0, we say x is in the code. If it's not 0, then x is not in the code. That's the test. So let me summarize. We really have two dual ways of characterizing a code, which you will see in the literature. We have a generator matrix. We might give a k by n generator matrix for the code. And then the code is specified as C is the set of all UG such that U and Fk to the n. K, F2 to the K. Sorry. In other words, this is an image representation. We take C as the image of a linear transformation. Call G a linear transformation. It goes from Fk to F2 to the K to F2 to the n, and the code is simply the image of this transformation algebraically. Okay, or we can specify it by means of a parity check matrix, H, which is the generator matrix of the dual code. So this would be the parity check matrix of the dual code, G. H is the generator matrix of the dual code, and we ask whether, now we specify it as I have up here, simply the x in F2 to the n such that x ht equals 0. And this is what's called a kernel representation, because it's the kernel of the linear transformation of a linear transformation defined by h2 from F2 to the n down to, this is a n by n minus k matrix. So the syndrome is actually an n minus k tuple. It's the elements of the syndrome are the n minus k individual bits, parity check bits. Okay. And sometimes it's more convenient to characterize a code in one way, and sometimes more convenient to characterize it in the other way. For instance, we were talking last time about the n minus 1, 2 single parity check code. or the even weight code, the set of all even weight n tuples, which has dimension n minus 1. And in general, for high rate codes especially, it may be simpler to give the parity check representation. What is the dual code? Let's call this C. C dual is what? C dual is what we call the N1N repetition code. In other words, it has dimension 1, it has two code words, the all 0 word and the all 1 word. Okay? Clearly, the all 1 word is orthogonal to all of the even weight words, and vice versa. A word has even weight if and only if it's orthogonal to all ones. So in this case, what is the generator matrix? We had a generator matrix last time consisting of n minus 1 weight 2 code words sort of arranged in a kind of double diagonal pattern. That's okay, but that's an n minus 1 by n matrix. Most people would say it's easier to say, okay, what's the parity check matrix? The parity check matrix in this case H is simply a 1 by n matrix consisting of all ones. And what's the characterization of the code? The code consists of all the words that are orthogonal to this. And that is why we call it single parity check code. There's one parity check, and if you pass the parity check, you're in the code, and if you don't, you're not. Okay, so that we see that these, first of all, here's an example of dual codes. Are their dimensions correct? They are. Is each one characterized correctly as the dual of the other? It is. So we've passed that. This is intending to make point C. It's a good example. Kind of one final thing is, suppose I have a code with generator matrix G and another code with generator matrix H. Are they each other's dual codes or not? And the answer is pretty obvious from all of this. Yes, they are. Let me substitute in here. X is supposed to be equal to UG. So another requirement is that UGHT equals 0 for all U. And without belaboring the point, if I have two codes with generator matrix G and H, they are dual codes if and only if they have the right dimension. One is nk and the other is n minus k. And we satisfy GHT equals 0. Basically, this is the matrix of inner products of the generators of C with the generators of C dual. And if we have k generators that are all orthogonal to these n minus k generators, then they must be the generators of dual codes. This is kind of intuitive and natural. All right, so again, this is a concise form that you would actually probably most commonly find in the literature. It's not hard to get to. Okay, so in this course, we're probably going to talk quite a bit about orthogonality. Duality is very powerful, but we're not going to be using it very much in this course, I believe. I'll mention duality whenever there's a duality property to mention, but in general, I'm not going to spend an awful lot of time on it. But it's important you know about it, particularly if you were going to go on and do anything in this subject. And, at an elementary level, it's nice to know that we have two possible representations, and one is often going to be simpler than the other. Use the simple one. In general, use the representation for the low rate code to determine the high rate code. Okay, any questions on this? I've now finished up the preparatory, yeah?
He's saying that every basis vector in G is orthogonal by V1 and H.
That's necessary and sufficient. Right. Okay, Reed-Muller codes. Why do I talk about Reed-Muller codes? First of all, they give us an infinite family of codes, so we can see what happens as n gets large, as k goes from 0 to n, whose parameters are sort of representative. They aren't necessarily the best codes that we know of. They're very simple, as I will show, to construct and to characterize their parameters, so we can do all the proofs in half an hour here. And they're not so bad. In terms of the parameters NKD, the Reed-Muller codes up to length 32 are the best ones we know of, at least for their parameters. There is no 3216 code that's better than the 3216-8 Reed-Muller code. There's no 32K8 code that's better than, that has K greater than 16, all those sorts of things. Actually, I'm not 100% sure of that. For short block lengths, they're as good as BCH codes or any of the codes that were discovered subsequently. For even longer lengths, up to 64, 128, 256, they are going to be slightly suboptimum in terms of NKD, as we'll see, in some cases. But they still are very good codes to look at in terms of performance versus complexity. The decoding algorithm that I'm going to talk about eventually for them is a Trellis-based decoding algorithm and maximum likelihood decoding algorithm. Within they can be maximum likelihood decoded very simply by these Trellis-based algorithms. And that's not true of more elaborate classes of codes. So from a performance versus complexity point of view, there's still good codes to look at for block lengths up to 100, 200. As we get up to higher block lengths, then we'll be talking about much more random-like, non-algebraic codes in the final section of the course. This is the way you actually get to capacity. You don't worry about NKD. Right now we're talking about moderate complexity, moderate performance. Okay, so they were invented in 1954 independently by Irving Reed and I think it was David Muller, D. Muller, in two separate papers, which shows they weren't too hard to find. As you'll see, they're very easy to construct. They're basically based on a length doubling construction. Now, let me start. So we start off with codes of length 1 or length 2, and then from that we build up codes of length 4, 8, 16, 32, and so forth. So in general, their lengths are equal to a power of 2, and m is the parameter that denotes the power of 2. So we only get certain block lengths, which are equal to powers of 2. They have a second parameter, r, whose significance is that d is 2 to the m minus r for 0 less than or equal to r less than or equal to m. Or some people, including me, are going to put the lower limit at -1 just to be able to include one more code in this family at each length. But this is just a matter of taste. You'll see this is a very special case, the -1. So let's guess what some of these codes are going to be. So we have two parameters, m, which can be any parameter, any integer 0 or higher. So the lengths will be 1, 2, 4, so forth, and r, which goes basically from 0 to m, which means the distances will go from 1 I'm sorry, from 2 to the m down to 1. And what are some of the basic codes that we're always going to find? Rm, we always write Rm of little rm. I'm not sure I completely approve of how the notation goes for these codes, but that's the way it is. So this is notation. That means the Reed-Muller code with parameters m and r. It's written Rm of Rm. All right, so Rm of mm. This is going to be a code of length 2 to the m and distance 1. What do you suppose that's going to be? This is always going to be the 2 to the m, 1. Sorry, the distance is 1. So it's going to be the 2 to the m, 1 universe code. In other words, simply the set of all 2 to the m tuples, which has having distance 1. Okay. Rm of m and, 0m. What's that going to be? This is a code now that has minimum distance length 2 to the m and minimum distance 2 to the m. We know what that has to be. It has to be the 2 to the m, 1, 2 to the n repetition code. Very low rate code, dimension 1. Okay. And then if we like, we can go one step further. There is a code below this code. This is the highest rate code you can get. This, however, is not the lowest rate code you can get. What's the lowest rate code? Of length 2 to the m? Well, there's one that has dimension 0. And minimum distance infinity by, I don't think I ever defined this convention, but for the trivial code, it consists of simply the all 0 word. What's its minimum distance? Undefined or infinity, if you like. So this is the trivial code. So if we want, we can include the trivial code in this family just by defining it like this. And it works for some things. It doesn't work for all things. It doesn't work for D, for instance. This definition holds only for r between 0 and m and doesn't hold for r equals minus 1, because there the distance is infinite. Okay, so let's start out and get even more explicit. We want to start with m equals 0. In that case, we have only Rm of 0, 0 and Rm of minus 1, 0. And this is going to be the 1 by either of these. The universe code is equal to the repetition code. It's the 1, 1, 1 code. And this is the 1, 0 infinity codes. And that's really the only two codes that you can think of that have length 1, right? This is the one that consists of 0 and 1, and this is the one that consists of 0. All right? I don't think there are any other binary linear block codes with length 1. All right, so that's a start. Not very interesting. Let's go up to length 2. So m is going to be equal 1. Here, Rm of 1, 1 is going to be length 2, and it's going to be the universe code, so it's only going to have distance 1. Rm of 0, 1 is going to be length 2, but it's going to be the repetition code. And Rm of minus 1, 1 is going to be 2, 0, infinity. Okay, so there are really the only three sensible codes of length 2. This is the only one of dimension 2. This is the only one of dimension 0. There are other ones of dimension 1, but they don't have minimum distance 2, so they're not very good for coding purposes. So this kind of lists all the good coding codes of length 2. All right, so now let me introduce the length doubling construction. Let me make the point, first of all, that all of these codes are nested. What does that mean? That means this code is a subcode of this code, which is a subcode of this code. All right, and that's going to be, in general, a property of Reed-Muller codes. We're going to get a family, and each lower one is going to be a subcode of the next higher one, which is going to be easy to prove recursively. All right. This is the key thing to know about Reed-Muller codes. How do you construct them? Once you understand the construction, then you can derive all the properties. It's called the U plus V construction for obvious reasons. Apparently, Plotkin was the first person to show this. I think Reed-Muller had 2 different constructions, and neither one of them was the U plus V construction. Reed, in particular, talked about Boolean functions. All right, but this is the way I recommend you can think about constructing them. And it's simply defined as follows. We assume we've already constructed the Reed-Muller codes of length m-1. It's a recursive of parameter m-1. Now we're going to construct all the Reed-Muller codes of parameter m, or length 2 to the m. And how are we going to do it? Rm of, we want to construct Rm of Rm. And we'll say it's the set of all code words which consist of 2 halves, a pair of code words, a pair of n-tuples of half the length. So it's going to be U, the 2 halves are going to be U and U plus V, where I choose U and U plus V as follows. U is in Rm of R minus 1 m. And so what does that mean? Sorry. It's got to be m minus 1, so it's got to be half the length. Is that right? R m minus 1, V is in Rm of R minus 1, m minus 1. Somebody who has the notes, like my valuable teaching assistant, might check whether I got it right or not. Let's see, what are going to be the parameters of these codes? They both have n equals 2 to the m minus 1. The distance here is 2 to the m minus 1 minus r minus 1, so the distance here is 2 to the m minus r, which is the distance that we want to achieve for this code. And the distance here is 2 to the m minus r minus 1, which is half the distance we want to achieve for this code. So we reach down. If we wanted to construct now a code of length 4 and distance 2, we would construct it from these 2 codes, the one of half the length with distance 2 and the one of half the length with half the distance, distance 1. So we would somehow use this to get a code of length 4 and distance 2, and we don't know yet what k is. Okay, so we're going to use these 2 codes to construct a larger code. Is the construction clear? All right. So let's now derive some properties from this construction and from the fact that we've started from a set of codes. Let's say we start from length 2 codes, or we could start from length 1. You could satisfy yourself that this construction applied to the length 1 codes gives the length 2 codes. I won't go through that exercise. So we have some set of codes m minus 1. What's the first thing we notice? Obviously, the length is what we want. because we've put together 2 to the m minus 1 tuples, and 2 times 2 to the m minus 1 is 2 to the m. So we've constructed a set of 2 to the m tuples. Length of the resulting code is 2 to the m. This is RM constructed in this way. Second, it's linear. It's a linear code. All we have to check is the group property. If we add 2 code words of this form, we're going to get another code word of that form. From the fact that these guys are linear, yes. Okay, so it is a linear code. That's important. Then we might ask, what's its dimension? How many code words are there? Do I get a unique code word for every combination of U and V? However you want to convince yourself, you obviously do. If I'm given this word here, I can deduce from it what was U. That's simply the first half of it. Subtract U from the second half of it, and I find out what V is. So there's a one-to-one map between all possible pairs, UV, and all possible new code words. And so what that means is, let me call it the dimension of the code with parameters RM, is simply the sum of the dimensions of the codes with parameters RM minus 1 and R minus 1, M minus 1. So, for instance, in this hypothesized code here, if I want to know the dimension, well, I take all possible combinations of words here and words here. How many are there? There are 8, has dimension 3. So I'm going to get a 432 code, which is not too hard to see as the single parity check code of length 4. All right. So that's how I do it. I simply add up the dimensions of the 2 contributing codes. Not a very nice formula. In the homework, you do a combinatoric exercise that gives you a somewhat more closed form formula, but I think this is actually the most useful one. In any case, we eventually get a table that shows what all these things are anyway. Now, just as a fine point, I want to assert that if I start out from a set of nested codes, then I come up with a set of nested codes at the next highest level. That, again, is sort of obvious. If these guys were nested, then I get the appropriate, if I take U plus V from subcodes, I'm going to get a subcode. That's, look at the notes if you want more than that little bit of hand waving. Okay, that's something I need for the next thing. I want to find out what D is. What's the minimum distance here? Of course, my objective is to make it equal to 2 to the m minus r. Did I succeed? What are the possibilities for U plus V? The possibilities are that they're both 0, or that this one is 0 and this is not equal to 0, or this is not equal to 0 and this is 0, or that they're both not equal to 0. And I'm going to consider those four cases. All right. Now, since every linear code includes the all 0 word, it's certainly possible that this comes out 0, 0. The only possibility for this to come out 0, 0 is if I choose U equals 0, then I have to choose V equals 0. All right, so there's one code word of weight 0 in my new code, but that's okay. All right, if there were 2 code words of weight 0, well, then the dimension would be wrong. This is, in effect, a proof that the kernel is just 0, 0, and so the dimension is okay. It's a one-to-one map. All right, so I don't really have to worry about that. I'm going to get one all 0 word in my new code. I can afford one all 0 word. I'm always going to have it anyway. It's linear. All right, so these are the more interesting cases. Suppose the first half is 0, but the second half is not 0. That implies that u is 0. That implies that the second half is just v, which is not 0. So v must be a non-zero code word in this code, which has minimum distance 2 to the m minus r. So in this case, I prove that the distance is greater than or equal to 2 to the m minus r. Similarly, suppose this one is not 0, but this is 0. Okay, if that's 0, it can only be because I chose u equal to some v. And that means the first half then is that v. All right, so again, v is in this code that has enough minimum distance. And so in this case, I prove that the code word has weight 2 to the m minus r. And finally, let's take the case where they're both not 0. In that case, u could be an arbitrary word in this code which only has distance 2 to the m r minus 1. So the first half is going to have weight at least 2 to the m minus r minus 1, but that's all I can say about the first half. But now the second half, what is this? This is a higher rate code than this. This, by the nesting property, is a subcode of this. So if I add a word in a subcode to a word in the code, I'm going to get another word in this code. So u plus v is still in this Reed-Muller code, still has a minimum weight if it's non-zero of 2 to the m minus r minus 1. So the distance is at least this in the first half, this in the second half, and that's, of course, still good enough. Okay? So by this construction, I've assured that I'm going to get a d greater than or equal to 2 to the m minus r. And of course, you can easily find cases of equality where it's only 2 to the m minus r. If this has a word of length of weight 2 to the m minus r, then you can clearly set up one like this that has weight 2 to the m minus r. Just pick one of the minimum weight code words as v, and u is 0. So the minimum distance is 2 to the m minus r. Alrighty. So those are all the properties we need. And then I like to display these properties in the tableau, which you have in the notes, which goes as follows. Let's just start listing these codes. Here are the length 1 ones. We only found 2 of them, 1, 1, 1, and 1, 0, infinity. So there are 2 codes of length 1. Now it turns out if you combine these according to the UU plus V construction, you get 2, 1, 1. 2, 1, 2. Where the weight 2, 1 is just you take the first half is 1 and the second half is 1. All right, so you can build this in the same way. And similarly, we can say just by definition, we're always going to put a universe code at the top and a trivial code at the bottom. So now I've listed all my Reed-Muller codes of length 2. Now to construct the ones of length 4, again, I'll put a universe code at the top, a trivial code at the bottom. I'll use my construction now to create a 4, 3, 2 code here. I'm just using all these properties. And down here, my construction, when you combine these two things, you always get a repetition code, again, 4, 1, 4. And I guess I haven't, I've hand-waved exercise for the student to prove that combining a repetition code with a trivial code under the UU plus V construction always gives a double-length repetition code. I mean, it's clear. V is always the all zero word. U is either all zero or all one. So we get two words, one of which is all zero and one of which is all one double length. All right, so now I can just go on indefinitely and without a great deal of effort. Here I find that k is 7 just by adding up these two things. That 8. This gives me an 844 code. This gives me 818 code, and similarly down here. And this, I now just turn the crank. 16, 16, 1. I always put that at the top. The next one is 16, 15, 2. Next one is 16, 11, 4. You know, after a while, you know, you don't know what you're going to get, but you get something. You've proved that all of these codes exist, that they're all linear, they all have the NKD that we've specified, and that furthermore they're nested. And a final property, which you might suspect looking at these tables, is that the dual of a Reed-Muller code is also a Reed-Muller code, and they're kind of paired up according to k and n minus k. So 15 and 11 is 26. 11 and 5 is 16. 5 and 1 is 6. 15, 32, 1, 32, and so forth. Now, do you see how I proved that all these codes exist? And if I continued, I could get arbitrarily long codes. One of your simple homework problems is just to do this, continue this for 64 and 128, see what additional codes you get. And so I now have this infinite family of codes that kind of covers the space NKD in some sort of sparse way, but it indicates how K and D go with N. And we come back to our original question, how well can we do with binary linear block codes? Well, here's some binary linear block codes, pretty close to the best we can find, actually. The ones I've listed up here are all as good as we can find. And how well can we do? You know, really, we don't need to know much to evaluate the performance of, say, 3216.8 code, which is now getting to be a pretty substantial code with 2 to the 16th code words, 65,536 code words. So we've built a fairly sizable constellation here in a 32-dimensional Euclidean space. And how good is it? You know, let's take 3216.8. Can I graph its probability of error per bit? Good estimate of it? Can I? Is there any information I'm lacking? Okay, I've been talking too long. Because I really like, when I go to the class, I'd like a little response. So you were going to say something?
We don't have k with the
Okay, let me tell you that the ND is approximately 600 and something. So let's say 630. It's probably not exactly correct. In the notes, I give a formula for ND. There's a formula that I don't derive that is known for Reed-Muller codes, and from that you can compute ND for any of these codes, just from the parameters MR. All right, so I'll give you ND as well. Now can I get the a good estimate for the probability of error per bit. And how do I do that? Union bound estimate. All right. So what's it going to look like? What are the two subsidiary parameters I need? One's the coding gain, right? What is the nominal coding gain of this 3216.8 code? Come on, this is not a difficult computation. Okay, what's k over n? 1/2. I think we can all do that one. What's the nominal coding gain? Take 1/2 times d, 8. So the nominal coding gain is 4, which is what in dB? 6 dB. Wow. Gee whiz, I've already got a nominal coding gain of 6 dB. Remember, my whole gap was, depending on how I measured it, 9 or 10 or 11 dB. This looks like already a sizable fraction of the gap with just this simple construction. Well, we better pay attention to this error coefficient as well, or the number of nearest neighbors. KB is, let's just take a rough estimate here. What's this going to be? About 40. That's good. It's just this divided by 16. So there are about 40 nearest neighbors per bit. How much is that going to cost us? That's a little bit more than 5 factors of 2. Right. Maybe 5.5 factors. It's less than 5.5. So this is very roughly something that will cost me about 1 dB. And so I get an effective coding gain of 5 dB. That's my first very gross estimate. All right, well, it's not 6 dB. It's only 5 dB. That's still not bad. Again, just if I really wanted to know what this was, I would write this out as 40 or whatever it is times q to the square root of 4 times 2 EB over N0. And can I plot that quantity? Yes, if I have MATLAB, or actually all I need is my baseline. So if this is my baseline, which went through 9.6 dB at 10 to the minus 5, then we remember how to plot that. I just take this whole curve bodily, and I move it 6 dB to the left. So I get the same curve. This is not very good, going through 3.6 dB. Fix it like that. How's that? Get it way down here, but then I also have to raise it by a factor of 40. So it really looks more like that. It's really going to go more through like about 4.6 dB or something like that. That's what these calculations are. Ashish took you through, I believe. And so, while 6 dB was my nominal coding gain, my effective coding gain is 5 dB. But still, hey, not bad. I've very easily been able to construct a code that gives you about 5 dB of coding gain. Is there any fly in this ointment? Can I just go out and build it now? Need a decoder. Who said that? Thank you. Good point. What's the decoding method assumed for this code? Excuse me?
Just a table right now, right?
Just a table based on what? I get some kind of received n-tuple, which is actually just a random, is some kind of vector in 32-dimensional space, 32 numbers, real numbers. And really, I'm assuming minimum distance decoding. So in principle, I want to compute the distance to each of the 2 to the 16th, 65,000 code words. And actually, nowadays, you might just do that. That's not a formidable task. Back when I got into this business, that would have been considered outrageous. But nowadays, you could keep up a pretty good decoding rate, even doing 65,000 distance computations and just finding the best one. That would do it. That would give you this performance. Okay? But, of course, we are going to be looking for somewhat more efficient decoding schemes than that. All right, so at this point, that's the only fly in the ointment. We have a way of getting this kind of error curve, provided that we're willing to do exhaustive maximum likelihood or minimum distance decoding. All right. And furthermore, we can continue. It's also instructive to see what happens as we let n go to infinity. What are we going to get with this construction? We pretty well know these are all going to be universe codes, which are not very interesting to us. They all have a nominal coding gain of 1 and are useless. They're basically just send a bit 32 times. Send 32 bits, I mean. Okay, what are these codes along here? Let me start there. These are all single parity check codes. What's the nominal coding gain? Well, as we get out here, what does the nominal coding gain approach? The code rate approaches 1. The code distance stays at 2. So the nominal coding gain goes to 2, or 3 dB, at a rate of 1 or a nominal spectral efficiency of 2. Okay, well, yeah, these are totally simple codes, single parity check codes. And even with that, it looks like we can get 3 dB of coding gain. But what's the number of nearest neighbors here? Number of nearest neighbors is just n minus 1 over 2. N choose 2. So the number of even dividing by k, which is n minus 1, we still get a kb that goes up linearly with n. So what's in fact going to happen to the effective coding gain? The nominal coding gain will go up and reach an asymptote of 3 dB. This is nominal coding gain. But somewhere out here, as this is reaching the asymptote, the effective coding gain is always going to be less, and it's going to have to bend over. And according to our rule of thumb, it'll eventually go back through 0 because the cost just keeps going up linearly in terms of kb. So the effective coding gain is not as great. It has a peak for some n. And so there's some maximum effective coding gain, which again I've left for you as a homework problem, that's less than 3 dB. And I'll give you a hint that it's of the order of 2 dB. It's pretty easy to work out, in the 5 minutes before the next class. Not a difficult problem to find out when this thing reaches its maximum. But still, these are very simple codes. We'll see if in a second. They have an extremely simple minimum distance decoding algorithm called Wagner decoding. It's just trivial. Not hard to do minimum distance decoding for these codes. And so, okay, not hard to get 2 dB of coding gain. What happens if we go along this line here? These are all codes of minimum distance 4. Again, let me start here. They're called extended Hamming codes. A Hamming code has minimum distance 3 and is suitable for hard decision, single error correction. These codes all have minimum distance 4. We've seen that it's always worthwhile to add an overall parity check to get an even minimum distance, and if we're looking at Euclidean space coding gain. And so these are actually slightly better than Hamming codes. They're called extended Hamming codes because they're Hamming codes extended by a single parity check, and they have one more unit of minimum distance. So again, asymptotically, these are called extended Hamming. The nominal coding gain goes to what now? The rate is again going to 1. Distance holds at 4, so the nominal coding gain goes to 4 or 6 dB. Well, again, the spectral efficiency goes to 2 bits per 2 dimensions. The nominal spectral efficiency rate to 1. But again, you have this kind of phenomenon, and I ask you to work that out also on the homework, where even though the nominal coding gain plateaus eventually at 6 dB, there isn't a maximum effective coding gain, which is something more in the range of 4 to 5 dB. You figure out what it is. And there's a limit to how much effective coding gain you can get with these codes. Does this all make sense? You seeing how I'm arguing? Okay. Here's another interesting sequence of codes. These are all half-rate codes, or nominal spectral efficiency 1 bit per 2 dimensions. I briefly mentioned that these things pair up in duals. The 16.5 code is the dual code of the 16.11 codes. If you see, there's a symmetry about rate 1/2 such that this is k and this is n minus k. And so you would suspect that this guy is the dual of this guy, which it is. This guy is the dual of this guy. This guy is the dual of this guy. And this guy is its own dual. It's a self-dual code of rate 1/2 or spectral efficiency 1. So these are self-dual codes. And what does their nominal coding gain go to? Well, the rate is always 1/2. 1/2 times 4, that's a nominal coding gain of 2. This has a nominal coding gain of 4. Next one in line would be a 128, 64, 16 code, nominal coding gain of 8. So the nominal coding gain actually goes to infinity. Gee, that seems pretty good. However, what is its true meaning? What we really want to know is what's the effective coding gain, and given that the nominal coding gain goes to infinity, is it possible the effective coding gain can get us all the way to the Shannon limit? Can we completely close the gap to capacity? As far as I know, this is an open question. I strongly believe that you go along this sequence, do maximum likelihood decoding, you will eventually get to the Shannon limit. That is the Shannon limit for this spectral efficiency, which is not the ultimate Shannon limit, but rather is 0 in terms of EB over N0. If you remember, for rate 1/2 or rho equals 1, the Shannon limit on EB over N0 was 0 dB. All right, you may or may not remember that. But so there's a question, does this take you all the way to the Shannon limit? And that would be a nice question for somebody to answer someday. I think it probably does. Especially in view of the fact that if you take this set down here, this will be a homework problem. This turns out to be a set of Euclidean images of these codes are biorthogonal signal sets. For instance, 32, 6, 16. What is that? That's a set of 64 constellation points in 32 dimensions. And algebraically, it's not hard to figure out that every one of these code words is orthogonal in a Euclidean sense to one another, except for one that's complementary, which is just what you expect in a biorthogonal signal set. So these give you biorthogonal. They're called biorthogonal codes, or first-order Reed-Muller codes, because the parameter R is 1 for all of these. What's happening to the spectral efficiency here? The spectral efficiency goes to 0. So these become highly inefficient from a bandwidth point of view, as we already know about orthogonal, biorthogonal, simplex signal sets. They use up a lot of bandwidth. But what else do we know about them? In this case, we definitely know that the effective coding gain does go to the Shannon limit. And in this case, the ultimate Shannon limit for rho equals 0, as rho approaches 0. So here there's a proof that these codes can get you to the Shannon limit. But it's, as we've already explained earlier, geometrically, it's at the cost of using much more bandwidth than you probably really want to use. But here at least is one capacity approaching set of codes just among these rather simple Reed-Muller codes along this line. And of course, we also see our repetition codes, our trivial codes. So this is a nice representative family of codes, and it really does tell you quite well what to expect. Are you looking at your watch? Thank you. Appreciate the hint. Didn't quite finish Chapter 6 today. Next time we'll start out with the penalties of making hard decisions, which at first blush seems like a not unreasonable compromise to make, but it actually costs a serious penalty. And that will finish Chapter 6. I'll do that as briefly as I can. And then we'll get into Chapters 7 and 8, which is finite fields, and Reed-Solomon codes, which are the single great triumph of algebraic coding theory. So, okay, that's tomorrow.